let's talk about current. Now, when physicists, what we now would call physicists, when natural scientists were looking at the flow of electricity, they weren't quite sure what exactly it was. They imagined initially that it was some sort of fluid like water in the sense that it would flow, and thus they used the term current. Now, current, the symbol that we typically use is I, or when we get to AC power, a lowercase version of that. And the formal definition is it deals with how much charge is passing by a particular point in a wire. So if I have a wire here, and I have current and I have charges passing by a particular point, then the current is basically the amount of charge that passes by this point within a certain amount of time, or if we're dealing with the instantaneous for the calculus-based group, dq dt. Now, when an electron actually moves past here, let's just be careful. This makes it seem like charges just flow nice and smooth through there, but in reality, a charge is going to move along, an electron, presumably, is going to move along and hit something, and then it's going to bounce, and then it's going to hit something else, and then bounce, and then hit something else, and bounce. And so the path is not directly in a particular, it's not in a straight line, but it has a general movement in that direction. And so the velocity of this, or speed of this electron, is known as v sub d, or drift speed. But it has an overall general approach going in one particular direction. So if I take a battery and I hook it up to a wire, I got my positive and negative side of the battery. I immediately, as soon as I make the connection, I have all these electrons, because the electrons are what is moving 99.9% of the time. The electrons immediately start to move out. Well, what allows them to move out is that I will have a charge here, a negative of an electron here, and the electron, as soon as it is allowed, is going to jump and bond with one of the positive charges on the positive side of the battery, and that leaves a hole. Now I have a hole, I have an electron that will then fill in that hole. And so now the hole moves this way. And so I have a hole moving in the direction of what we call the current flow, and I have electrons moving opposite that. Now some textbooks will talk about electron current and traditional current. I tend not to talk about electron current, other than I do recognize electrons would be traveling in this drawing right here. Electrons travel this way, but the current, what we call current, is flowing the other way. Because again, thinking back to the water flow, water flows downhill. It flows from a higher potential energy to a lower potential energy, or in electronic language, from a higher potential to a lower potential. Later they discovered electrons, but the convention had already stuck. And so current flows from the high side to the low side, even though physically what's usually happening is electrons flowing the other way. Now I do say usually, probably for almost everything that you're going to do, future engineers, anyone except for physicists, we are dealing with almost everything that you will deal with. The electrons are things which are actually moving here and not the protons. In high energy physics, you will get evacuated tubes and you will shoot protons through the tubes, in which case you'll have a charge because a positive charge is moving. And you can get those easily enough by sending a hydrogen atom through a strong electric field, which will then split the atom. That's probably a bad wording there. It will separate the electron from the proton, so you can have a bunch of electrons or a bunch of protons there. So this is current. Just a quick example. I have 5 times 10 to the 10th electrons flowing to the right in some wire every 15 seconds. What is the current? Well, I have electrons flowing to the right, so my current will be flowing to the left. And the charge, I have 5 times 10 to the 10th. Probably the biggest mistake I see students making is they assume that is Q. That is not Q. That's just the number of electrons. So I have to figure out what my charge is. 5 times 10 to the 10th electrons times 1.6 times 10 to the negative 19th coulombs per electron. Officially, it's not a conversion, but the math-wise, it looks a whole lot like one. And so do the little math here, 5, 10 negative. Let's try that again. 5 E10 and 1.6 E19 negative times. And so our charge that's passing by is 8 times 10 to the, unfortunately it doesn't put this in scientific notation, so 10 to the negative 9th coulombs every 15 seconds. And so the current in this particular case is flowing to the left, 8 times 10 to the negative 9th coulombs over 15. And what we end up with is 0.533, that's 15 seconds, nanoamperes, which is a really small current. I'm not sure you would even notice it if it were running through you from some external source. And that is the basics of current.